Let's work through a couple more examples of RC circuits where we have both resistors and capacitors in our circuit to make sure that we've got enough practice for these. For number one, we're determining the equilibrium current in the circuit and the charge stored in the capacitor. When we're at equilibrium, remember the capacitor is charged, so current is 0. The initial current is simply the voltage divided by the resistance, so I have 3 amps. The charge stored in the capacitor is the capacitance times the voltage. So we have a 3 farad capacitance times 6 volts, and so we get 18 coulombs of charge stored. For number 2, we want to determine the initial and final currents in the circuit. We want to determine the charge stored in the capacitor. So basically the same thing. Again, the initial current is simply the current through the resistor, and I'm going to find that by taking the voltage divided by the resistance, and guess what? It's the same 3 amps. Again, when the capacitor is charged, that's at equilibrium, and my current is 0. Charge stored by the capacitor, again, 4 farads, 6 volts. So again, I have this time I have 24 coulombs of charge stored. Let's take a look at the next one where it's a little bit more complex. So we're going to work through this circuit on the left, and we'll take a look at the circuit on the right as an example in class. So I want to determine the equivalent resistance, first of all, and I should probably also determine the equivalent capacitance. My resistors are in series. So I have a 3 ohm resistor plus a 4 ohm resistor, so I have a 7 ohm equivalent resistance. My capacitors are also in series, and for capacitors equivalent in series, it's going to be 1 over, so I have 1 over 10 millifarads plus 1 over 5 millifarads. So 1 over 10 plus 2 over 10. So my equivalent capacitance is 10/3 millifarads. Determine the equivalent current in the left circuit and the initial and final currents in the right circuit. So we're going to do this first part. Equivalent current in the left circuit. Well, current can flow through the circuit the entire time because the capacitors are in parallel with the resistor. So the equivalent current, or the total current actually in the circuit, is going to be the total voltage divided by the equivalent resistance. So I have a total voltage of 15 volts. I have an equivalent resistance of 7 ohms, and so I get 2.14 amps. I have a voltmeter across each resistor. I have 2.14 amps through it, so the voltage in my 3 ohm resistor is simply going to be the 2.14 amps times the 3 ohms, and I get 6.42 volts. The voltage across my 4 ohm resistor is going to be the same thing, current times voltage, and I get a voltage for this one of 8.56 volts. Charge on each capacitor. Well, the equivalent capacitance times the voltage gives me charge. My capacitors are in series, so my 10 millifarad capacitor charge is equal to my 5 millifarad capacitor charge, and that will be the equivalent capacitance, which is 10/3 millifarads, times my voltage across that branch. The voltage across that branch is the same as the voltage across the 4 ohm resistor, so that would be 8.56 volts. And so I get 28.5 millicoulombs of charge. We'll work through the other circuit in class, but that gives us an example of how to work with capacitors and resistors when they're in series and in parallel and in more complex circuits. And that takes us through chapters 19 and 20.